Hello, in this chapter, we want to learn how to represent a wide sensor stationary random process using its power spectral density. These representations could have various applications and is a fundamental basis of signal processing. So a spectral representation is that you have a random process and then you want to x of t, and let's say you have its power spectral density x of, let's say, omega, and you want to represent these. So applications could be in compression of signal x of t, it could be signal enhancement, signal storage, signal recovery, or representation of signal applications in speech, in speech recognition, speech enhancement, video enhancement, and so on. So various. So a spectral representation is a powerful tool which allows us to decompose and stochastic processes for efficient use in different applications such as estimation, detection, and so on. So in this chapter, we consider, in this module, in this course, we consider only wide sensor station random processes for spectral representation. So we will learn how to find an LTI filter which has an impulse response of LFT. So using this LTI filter, which is not random, and a white noise. So if you have a white noise I of t given to this L of t, then it will produce x of t. So given an x of t to be wide sensor stationary, we want to find this filter and this white noise. This white noise is referred to as innovation process, and so you see the white noise given to innovation filter produces your random process. So these two together can generate your random process. So the inverse of this filter, inverse of the innovation filter, can produce the innovation process. So this is called innovation process. Is the component of the input which is new. And this is whitening filter because this random process is not white. So when you apply to this becomes a white process, white noise. So it will convert your random process to white random process, such that using the white random process and this deterministic filter, you can reconstruct it back. So this relationship that this should be white, its power spectral density should be delta t, and then you have L of t and so on. So you writing the power spectral densities relationship between these three autocorrelation functions, and we have three. So we get two equations, and then we'll be able to solve this problem. So you represent x of t by this filter L of t, and this filter should be causal and stable, so two property, and also invertible, because if its inverse exists, then you can use that. So if it is invertible, you can apply x of t to this invertible filter, get I of t, and just, for instance, in communication, you can just send I of t instead of x of t. And then transmitting I of t may require less bandwidth, less energy, and so on. So in this case, we say that x of t is represented by the impulse response of L of t and of t. So the pair of L of t which is the innovation filter, and the white noise, I of t, can produce x of t and vice versa. So this is why we call this as a representation. In some application, for instance, in speech processing, lots of information in I of t is barely noise. So sometimes, quite often, the noise I of t is heavily reduced, and then not all information about I of t is transmitted. Same thing for videos and so on. So interestingly, you can represent a spectrum of x of t using this equation by parameters of the impulse response of the filter and only the variance of the input. So what we can do, we can make this innovation filter a parametric filter, so like finite order, and using those parameters we can adjust, and then this filter is the inverse of this one, so there is a relationship between these two filters, and this is called a spectral representation. So a process x of t, which could be represented, is called a regular process. If a random process could not be represented by a causal, stable, and invertible filter, is not a regular random process, and therefore you cannot represent it. So usually we work with representable random process, which we call them regular random processes.